Hello everyone, this is another Abaqus tutorial. In this tutorial we're going to conduct a pushover analysis on concrete shear wall, but in previous tutorial we used solid elements for the concrete and also truss element for the rebars. But in this tutorial we are using plane string technique, which is a type of shear element in a 2D form. This technique is quite fast, and it requires less computational time, and the result is, if you model correctly, so the result will be quite accurate, and you can obviously see the crack propagation and failure modes. At the same time, you can use CDP material or concrete damage plastic model for plane string technique as well. So as example, we have a concrete shear wall. We have with this dimension, which total height from this point to bottom of the foundation is 3 meter 40 centimeter or 3,400 millimeter, and the thickness of the shear wall is about 200 millimeter. The weight of the shear wall is about 1,400 millimeter, and the foundation we have 600 millimeter height, and the toy size is 300 millimeter, and the depth is we can say the weight is also about 400 millimeter. So the concrete is made concrete C30, which has a equal 30 megapascal compressive strain, and the rebar, we will arrange the rebar as about 100 spacing in the vertical direction and 100 to the horizontal direction. But we're not considering the rebar in the foundation because, as we know, the stiffness of the foundation is quite high, so damage will not be considered here, but instead it will be here. We make quite simple. This is not a verification work, just as a random example, and show you how to use plane string and how to assemble rebars with the 2D plane string modeling technique. So we jump to the program and we quickly draw the part. In the part we use concrete shear wall, which is total concrete shear wall, and we're gonna use a 2D planar, and for maple you can use shell elements, and you can approximate the size. You can give about 4,000 or 6,000. And the first thing is I'm going to draw the foundation 0.01 and about 2,000 meter in the x direction, and the height is 600 mm. And now we draw that foundation. The second, I take a polyline and then draw one point here and then a snap. So the first point is about 300 in the x, 600 in the y, exactly that point. And the total I, again 300 in the x, 300 in the y. Now we are here, and 130 and 30, 140 plus 30 will become 1,700, and equal to the height of the structure, and we can drop it here. And now we wanna delete or remove this part, and we're gonna keep it like this. So I want to make a small partition that the shear wall and the foundation should be distinguished by this, and I can use I don't need to a partition. I'm just going to draw a line here. If previous was with this, so we cannot actually do partition, but instead it will not giving error. So now we can complete. You see here, and we have foundation, and also we have shear plate or shear walls. And the second part is we're gonna draw the longitudinal rebars. Longitudinal rebars, we assume there is a diameter of 200 millimeter in the vertical direction. So we use the same planar and wire, and it's equal to the height of the total structure, 0, 0 and 0, 340. Now you can see we have drawn the longitude. The horizontal is equal to the weight of the shear plate or shear wall, and I'm going to call transfer rebar. The same method, and size is 1400, 0, 0, and 1400, 0, and here. So in the foundation we do not have vertical rebar. You can add in case if you want to verify or simulate an experimental work, then you can add to. Now we have generated everything, and we can go to the property, and we're defining material. So we're using CDP. I already have some material in my library. You can add your material in concrete, and here is CDP 30. And also we have some steel material. Steel is, this is a Chinese steel, structural steel, and we can check it what's inside. Its density 7.85 equal E minus 9, and elastic and plasticity is this one. And the same thing for the CDP material. You can see there is a lot of tutorial on CDP. Even in my YouTube you can find it, how we can determine these things. You give the density of the concrete, elastic modulus can be calculated by simple equation, and concrete damage plasticity. Here is the plastic. This is the default parameter you can get from the Abaqus documentation, and the compressive strain, which is taken from the test and then converting to the through stress strain and elastic strain, and including you put some damage parameters here as well. The same thing for the tensile behavior, and it's about 30% of the compressive strain, and the same thing for the tensile damage, like this. So, okay, the material is okay. Now we want to define some section. The first thing is that let's call it concrete wall. The first thing is concrete wall. We're using solid and solid homogeneous, and so the plane strain is also solid, but it's a plane strain. We use concrete, and here I take the plane strain thickness, going to be 200 mm. And we can take another one we called the foundation, and the foundation is the same technique, but the depth is 400 mm. Now we want to define the rebar. The first thing is rebar for the longitudinal, which we want to use T rebar 20 mm, and it's a beam using truss element. So we take the steel, and the area of the rebar 20 is 314 square millimeter, and okay. And the same thing we're gonna call rebar for the horizontal direction is rebar 10 or transfer rebar, and the same thing. And this is 78 point, actually, like this, pi d square per 4. You can use that equation. And now we want to assign those sections to the elements, and we have rebar 10 for the horizontal transfer, and we have rebar 20, and we have the concrete shear wall. The first for the concrete wall, which is 200, and the second is here, and we're gonna concrete foundation 400. Now we have finished the material assignment, and there is nothing, and we go sort of the assembly, the third part, and we bring the concrete shear wall first. The second, we want to bring the longitudinal rebar here, apply, and we want to bring the transfer rebar as well. Okay, and I'm gonna move this one exactly from this point to this point, and you can use these things, and you can see different color. So I'm gonna make it something else. I'm gonna take this, putting inside a little, so just generating the clear cover for the shear wall, and not from the top and bottom. That doesn't affect, because this boundary condition, top is also boundary condition, such as we applying load testing, but in this area we should consider that. the point is from 0, and we're just going to in the x direction by about 50 or 5 centimeter, only CV 50 millimeter. And we want to duplicate this, or we want to generate a pattern and taking this one, and it's be 100, and this one will be 1, and we're gonna take this one and going to yeah. Now we have distribute the longitudinal rebar, the entire shear wall, and okay, and we are going to do the same thing for the this rebar as well, and that's here. And I should say that it's better to reduce the size of this shear rebar or transfer rebar is better, in case we can just generate the meshing area here. But if we extend, it's okay, no problem, because so that doesn't have so much impact. But the longitudinal lift should be here. That will be some impact. We're gonna make it let's go to the part, and we want to reduce by 100, and we can edit this here and just click that one, and we're gonna resize it, and this is 1300. So we reduce by 50 and make it equal to the longitudinal bar weight. Now we're done here, and okay, apply, okay, and we go to assembly, and you can see we're gonna go to section. It's better, you can see obviously in the section, and I'm gonna select this one again, and this time I will bring it here, and I'm gonna take one more time and drop it down, bring it down about by 50, and the first point is 0, 0, and the second point be 0 minus 50, and you can see we are here, and the same. So I should take it again, and 0 and 0 minus 15. We should say okay, we're done. Now we want to use a linear pattern and take this direction, and we're gonna give 100 in opposite direction, and we're gonna make it 1, and we're gonna extend it to the bottom of the concrete. We also can put inside, it doesn't matter. So now we are done. The reinforcement is added to the structure. So what we're gonna do is we quickly generate a seat to because we will need it. We call rebars, and I'm going to come to here and just concrete shear wall are going to be removed, and the remaining should be rebar. And again, I'm going to cut everything, and this time we're gonna replace this one, and we wanna create another seat. We call it concrete, and here we are. Now we have finished the assembly. One thing I should say here is the loading part. In practical and experimental work, when I have done, is there is a steel plate or a steel plate. Then the steel plate is attached with this area, and then the actuator will be applied in this area, and the structure will go back forward or push just in one direction. And now we also have starting to add a sort of a rigid element in this point, and that will be very perfect. But we're not going to do just be considering applying the load in the top of this beam, this element. So we keep that as the same. Next, we're going to step. We call it, the step is just a pushover static, nonlinear static analysis. We're going to call it nonlinear static analysis, and we consider to be general static, and we want to take the nonlinear. You can increase the time period based on some judgment you have. I keep it 10 seconds, and we're giving a large number in case if there is required more increment, so you're not giving this, you're not receiving this error. So I'm giving 10,000, maybe in 1,000 we will finish. and this should be 0.1, a small number to begin, and also this should be not take error, giving a small number too, and this will be 0.01 maximum. So OK, and we also can edit the output, and because we have defined the damage, so we need to check the damage, and we also can use this one, which is color shear, color stiffness degradation. Okay, and before we go to the time history output, I'm going to the mesh, and I want to generate some mesh for the structure part. And the first thing is you should define the type of element this element is. It's a trans element, and you must give a proper meshing. So I'm going to give 200. 200. That 130 is okay, which is 10 element. If we give a small mesh, so the computational time will be quite large. And the same for computational rebar, and we're gonna give this one, which is twice of that, and I'm gonna make it this one a little smaller. This suppose that's 114. Okay, now we are done here in this one. Just going to mesh it, and we are in the shear wall. To get a better mesh, the first thing is you should define a proper mesh. Quad dominated mesh is not good mesh. You can use quad better with middle axis free and giving proper. So this supposed to be 100 is not bad. If we're giving 50, that will be much more better, but it will take a lot of time. So for this study, just 100 is enough for us. And yes, you can see the entire element is there. So here I want to create a seed we call the node, displacement node, taking node, and I'm going to take this node. Or if I want to add actually like me displacement, I'm going to take this one. Well, that's okay, that will last. Now we are finished, and we go back to that step, and we want to generate one output which is called the displacement force displacement curve. So taking that displacement point, and we don't need the energy, and we go to the REF2 and we the same direction. You also can take this one in case if you want to reduce the time of analysis, you can change this. That's one little. Now we should define the interaction between concrete and rebar as the same as the solid element or solid element, and we're going to come to the embedded region, and here is the seed we already defined. We want to embed the rebar inside the concrete, and we want to take concrete. Now we're done here, and we finished interaction, and we're going to go to loading. We don't want to apply any gravity load. We don't want to apply any gravity load. We just want to horizontal load. In case of some sort of experiment, you can also apply it if there is any gravity load. So the first thing is I'm going to define a boundary condition in initial, and I'm going to use this one. And so we don't need here. I'm going to grab this bottom of that. Here, it's not good. It's not good. I'm going to generate another set. Create. I'm going to call node and called fixed, and here is fixed, and here I'm going to again create that boundary condition and taking that set which is called fixed, and I'm going to fix it in all two directions. And the last one is going to the nonlinear static analysis step. We're applying a displacement in this point. So the displacement, the total height is 2.8 meters, so we want to take it about 3%. So 0.3 times to 8,000. This is 3% of the drift. So okay, if we see how much is 84 millimeters. So it's okay. Now we are done here, and we quickly go to that analysis. We just submit the job. We're gonna call it pushover plane strip. Okay, plane strip. So the analysis is submitted, and we want to check it's running, and if there is any error to fix. So unfortunately there is no error, and the program is running, and we can wait for a while to see the result. So it's a lot of element nodes, and it takes at least 2-3 hours to complete. Here is one thing I want to say you. During the analysis or the program is running, suddenly the program will stop or not showing because the list graphic, and it will start to work on the background. So we have saved, or we have submitted a job called pushover plane lesson, and it's running in the background. But now we don't know how much time is passed or the analysis completed. We should wait about hours to finish. Now we're gonna open this ODB file, which is the result, and I want to see what happened and what's the result. Now you can see the ODB file is open, and we can see the increment is 3,242, quite large increment, and the time is from 10 seconds is 3.22 seconds. So now we go to the deformation, and we can see the deformation how it looks like. So it's not showing. Wait. And we should just change 1 2 step. Okay, we can just remove the concrete or rebar. You see the rebar replace. Yeah, here is, you can see the rebar, and so it's quite running and taking a lot of computer space, and also the computer RAM and graphics, so it takes a little time. Yeah, it will be responding. And now we want to see some concrete damage. Go to showing all, and we come to the concrete damage, and we expect this area should be damaged, because when we push, this area will be in tension, and you can see the damage is exactly as we expect. And so we want to check the compressive damage should be this area, but there is no any compression because the compression is not reached. And we also have some other parameter you can see, such as the displacement. And the top area is quite large displacement. If we go to the U1, U2, U1, sometimes doesn't showing because we should change one step more. Yeah, now you can see this area is quite large, and this is lower, and the bottom is 0. Now we want to see the pushover curve, and we come to here. From here we want to generate pushover curve. So the analysis is not completed, maybe this giving data is maybe not accurate, and we want to generate from other point. So here we have ODB file, and we want to select unique node, and we want to get the reaction force in one direction and in this direction, and we want a displacement also in this direction. So but first, I'm not going to add this one. Come to here, there was a node we called base or fix this area. So I'm going to save it. We're gonna use a function called sum, because there is a lot of nodes, and we want to get the sum in just here, so that the sum of those nodes is generated automatically, and it takes some time. So the 3,000 point is quite large, and it's a lot of nodes take some time. And now it takes 7%. So you should use in the time history output, you should use output based on the time, like 0.01 second, so that 10 second will be about 1,000 points. So we don't need too much point, and this causes a lot of problem or issue during the analysis. Okay, now the reaction force is generated here, and we want to come again here. We want to turn off this one, and this time we're going to take U1 and taking no displacement, and we want to save as it is. And the same thing, it will take time to extract the data. Now the displacement is also generated here, and we can operate in XY. So we have combine, and we take U in the X direction in axis, and force in the Y axis. So we're going to plot it, and sorry, that should be vice versa. Force, displacement. Yes, we should do one more thing. We should times -1 because it's in opposite direction. So we go back to here, and we're going to delete this one, and we're going to again combine, and this time we're going to using combine minus 1 times displacement in the positive direction, and we're going to just note this one, comma, and minus 1 times RDF. Now we are okay. And save it. You can call FED, force displacement curve, and just here and plot. And now you can see here is the curve. This is the force displacement curve, and going to like this and here. So it's almost 250 kilonewton maximum capacity, and the maximum displacement is 25 millimeter, almost about 1% of the drift. You can manipulate this data, and also you can see the some other parameters, such as the peak equivalent plastic equivalent strain meter, these things. And finally, this is the end of the tutorial. If you have any question, please put in the comment. I will find time to answer you. See you next time.